Hey y'all, welcome back. Today we're going to start a new unit, and this unit is going to be all about solving equations, particularly ones that have the trig functions kind of buried inside the equation. And for most of these, your unknown is going to be inside the trig function itself. So we'll solve equations like you see below, like sine of x equals 1/2. Now we've solved ones like this back in Unit 1 within the context of trying to find a missing angle measure, where we would set up our ratio and we would take the inverse trig function and we'd use the calculator to find whatever that angle measure would be. Now here we are not going to be using calculators because we don't really need them, but what we will use is the unit circle to help us answer this question. So like if you look at the unit circle, what we're really trying to find here is what angle measure is going to make this statement true. Sine of what angle is 1/2. And if you look over to your unit circle over there, you'll see that there are two coordinates where the y coordinate is 1/2. Remember that the sine is opposite over hypotenuse, and the opposite side correlates to the y coordinate. So if you look closely, it's happening at pi over 6 and 5 pi over 6. I can't really mark on this little picture over here, so I'm going to hide that for now and bring up this interactive unit circle. And what we're looking for is, since remember sine is opposite over hypotenuse, and the hypotenuse is 1, we're really just looking at the opposite side, and we're waiting for this y value over here to become 1/2, and we're interested in what the angle measure is. So we get to about here, and we see, this really should be exactly 30 degrees. Let's see, well, we get it close enough, but just look at this radian measure right here, pi over 6. At pi over 6 radians, the y value is 1/2. And we could see that the y values, there's going to be two of them, right? There's one right here, there's one over here. So if I let my terminal side continue to rotate, and I get to over here where the y value is 1/2, I can see that my other solution is going to be 5 pi over 6. So initially, I might just say, okay, well, there are two angle measures here where sine of an angle measure is 1/2, and that would be pi over 6 and 5 pi over 6. And that doesn't like my pi's there. So let's go ahead and make that look a little better here. But these are going to be two solutions that will satisfy the equation. But what we'll see here in a second is that there are actually many, many more. So like I said, we solved something like this in the first unit, but in the second unit, in the last unit, when we were graphing functions, one of the things that we learned is that these functions are what we call periodic. And what I mean by periodic is that there is a portion of the graph that just kind of repeats itself over and over again, and we see that happening along the unit circle, after we go through one full revolution. So in terms of pi, or in terms of radians, we have pi over 2, pi, 3 pi over 2, 2 pi. But we could keep going. And if we keep going like an extra pi over 6 here, we're going to get another solution at what we would call 13 pi over 6. And we get another solution over here if we add 5 pi over 6 to 2 pi. And then we get another one. As we keep rotating, we get more and more solutions. We can see that a little bit more clearly if we graph y equals sine x. So here's our graph of y equals sine x, and we can see it's periodic. If we just plot, if we look for where the value of the function is 1/2, which I guess would be right about here. Let's try to zoom in a little bit so we can actually see where 1/2, oh, nope, I used the wrong zoom in button. That's too much. There we go. So if we see that there's going to be two values where the y value is 1/2, and what we saw on the unit circle is that it's pi over 6 and 5 pi over 6. So let me plot those. There you go. So this point right here is, it'll let me grab it. There we go. Pi over 6 comma 1/2. So we know sine of pi over 6 is 1/2. We also know sine of 5 pi over 6 is 1/2. But what we don't have marked is that there are more places where the y value is 1/2, where sine of theta is 1/2. In fact, there's infinitely many. If I continue to graph some of these, like I said, 13 pi over 6, that's going to be that point right there that just popped up. And then the next one was, what was it? 5 plus 12 is 17 pi over 6. Let's see if that's right. 17 pi over 6 comma 1/2. Yeah, it's just 0.0. Oh, you can't see it. Let me zoom out just a tad so you can see that. My bad. So over here, like this last one was the 17 pi over 6, and this one over here is the 13 pi over 6. And you can see that we're going to have infinitely many solutions. If I just like keep dragging this over, you can see that all of these points that lie along y equals 1/2 are going to be solutions. So we're going to have infinitely many. So I'll go over how you're going to write all of that because it can be a little overwhelming when you realize there's going to be infinitely many solutions, right? But depending on how the question is worded, we might answer it a little differently. So it's like not only do we have all these two, but we have lots of others. Okay, and we'll get into how to find those here in a sec. All right, so let's look at the strategies we're going to use to actually solve some of these equations. So let's look at one that's kind of similar to a linear equation. At least for these first few problems, I want to first solve a linear equation or a non-trigonometric equation and show you how a similar equation that, instead of just having x as something like cosine of x, how we answer that. So, if this was just a linear equation like back in Algebra 1, this is just a real basic two-step equation here, we would start by subtracting 4 from both sides, and that would result in root, if it'll let me type, come on, there we go, root 2x equals -1, and then we would divide both sides by root 2 here to solve for x. So divide by root 2, divide by root 2, and then so we get x equals -1 over root 2, which would, once we rationalize the denominator, become root 2 over 2. Okay, so this would be our solution if this was our equation. Just a real simple two-step equation here. Take care of our, where is it? There we go. There we go. We would subtract 4 from both sides and then divide both sides by root 2, just like that. So if I'm going to solve a similar equation, but instead of having x, I have cosine x, I'm going to essentially just take the same steps, okay? All the things that you learned in Algebra 1 and Algebra 2 are still going to apply here. So I'm still going to subtract 4. Really what we're doing here is we're using these properties of equality, which you may have had to cite back in geometry. And so here we go. So after I subtract 4 from both sides, it becomes -1, plus 4 goes away. Then I'm going to divide both sides by root 2. And what I really want to emphasize here is that as you're solving, your goal, initially at least, should be to isolate your trig function. Okay, don't get hung up on trying to get x by itself right at the beginning. Instead, got to be outside there. Instead, just get this by itself. So you can see like these are solved like basically the same, right? Like you subtract 4 from both sides, you divide both sides by root 2. The only difference here is once you have your trig function isolated, now we can try to find x. So we can look at the unit circle. Now let me pull that up, move it over. And we're looking for the coordinates, the angle measures where the x coordinate is -root 2 over 2 because the cosine is looking for the x coordinate. Like if I look back at this little interactive unit circle, we're looking to see where is the x value -root 2 over 2. So that's going to be like approximately here. The x value you can see is -root 2 over 2. The angle measure here is going to be 3 pi over 4. And then if I bring it over here, I'll find the other one, which will be at 5 pi over 4. So we're looking at these two angle measures are giving me an x value of, oops, I don't know why, didn't know I could actually grab that, where the x value is -root 2 over 2. So I'm going to report those two values on the unit circle first. I'm going to say x equals, what did I say they were? 3 pi over 4 and 5 pi over 4. But as I was talking about earlier, these are not the only two solutions. So it kind of depends how the question's worded here. Sometimes the question will say something along the lines of, and I'll just type this out, is, solution, find the solutions on the interval 0 to 2 pi. Steal this little pi over here. Oh, I don't know if it's going to let me do that from here. I might have to grab it elsewhere. Yeah, didn't like that. So it's all right. I got a pi around here somewhere. Let's try this over here. Yeah, there we go. Okay, so solutions on the interval 0 to 2 pi. Can we make that a little bit bigger? Is it going to let us? There we go. So in other words, what this is saying is these are the solutions that exist on the unit circle itself, and we're going to sort of ignore all the negative solutions and all the solutions that are greater than 2 pi. But sometimes I'll want the general solution, okay? In other words, I want all possible solutions, which, as we saw earlier, there's going to be infinitely many of them. So in one way, it might say all possible solutions. Another way we might say this is it's the general solution. In other words, this is going to be like the solution of all the solutions. It's going to be a much better answer here. Usually in the directions, I'll ask for one or the other. I'll say, sometimes I'll go easy on you and say, hey, just give me the ones that are on the unit circle. But some cases I'll be like, no, I really want you to tell me all the solutions. So let me show you how you would write that. So as we know, the period of this function, sine and cosine, is 2 pi. These values will repeat every 2 pi. So like if I add 2 pi to this point, pi over 6, that's going to take me to 13 pi over 6. And if I add 2 pi to this one, it's going to take me over here. And I can add 2 pi again and add 2 pi again and keep getting more and more solutions. I could also subtract 2 pi and move to the left here. Like if I subtract 2 pi from both of these x values or theta values, that'll send me over here. And if I do it again, it'll send me over here. And I'll just keep getting all these other solutions. So the way to write this is going to be to put both of these in these set brackets and say, okay, both of these are solutions. And to get more solutions, I'm going to add 2 pi, okay? But not just 2 pi, because that's only going to give me like one more set of solutions, but I'm going to write 2 pi n, and the implication being here is that n, well, let me just write this in text. The implication being that n could be any integer. In other words, like just to kind of explain this a little better, I could add 2 pi, I could add 4 pi, 6 pi, 8 pi. Basically, this number could be any integer. It could be 1, 2, 3, 4, 5, 6. If it's 1, then I'm just adding 2 pi. If it's 2, 2 times 2 is 4 pi. 3 times 2 is 6 pi, and so forth. This also takes care of your negative solutions as well, because if n could be any integer, it could also be a negative number. Like if this is -1, then adding negative 2 pi would be the same as subtracting 2 pi. So this grabs all of them. And so your general solution is going to look like this. And the whole point of writing it like this is that we grab every single solution there is rather than just the ones on the unit circle. So when you get your homework tonight, you're going to notice like sometimes the directions say, give me just the solutions on this particular interval. And sometimes it'll say, give me all the solutions or give me the general solution. And so you would write it like this. Okay, so we've kind of covered a lot here. We went over just the fact that you solve this very similarly to a linear equation. And I also went over the 2 different ways how you can write your solutions. Whether I'm just getting the solutions off of this particular interval or if I'm finding all of the solutions. Let's look at a problem that's a little bit more complicated. This one is going to be more similar to like a quadratic equation, but again, I'm going to show you kind of solve it the same way. So like if this was just a regular old quadratic equation with no trig function, I would start by adding 3 to both sides, which is exactly what I would do over here. Okay, so I might as well just like solve these at the same time. And then I would get 4x squared equals 3, over here. Over here I would get 4 times the sine squared x equals 3. By the way, I just want to like really kind of mention this notation here. If you see like sine squared or cosine squared like this is really like saying sine x times sine x. Okay, sine x times sine x, where you're multiplying the sine x by itself. So it's kind of like saying like x squared is x times x. Why the exponent is here rather than out here? Well, I think the reason to do that, this one actually has a pretty good reason, is that if I put it out over here, then it's not super obvious whether I'm squaring the x or whether I'm squaring the function. But if I put it here, it's very obvious. There's not really any way you could misinterpret that because you don't see an x squared. So it's actually a pretty good notation there. Okay, so the next step would be to divide both sides by 4. Right, so I'll go ahead and do that. I'm going to divide both sides by 4 here, and I'm going to end up with 3/4 on the right-hand side. I'll do the same thing over here, just so you can see that the way we're solving this is identical. So here we get x squared equals 3/4. Okay, no big deal. Over here we've got sine squared of x equals 3/4. And think about what we would need to do next here. Okay, so we've got x squared equals 3/4. What we need to do is take the square root of both sides and then include a plus or minus so that we don't forget about the possible negative solution. So we'll have x equals, do I have a plus or minus symbol here? Come on, Cami. Yep, we got it. Okay, so plus or minus the square root of 3/4. Now we will simplify that, but I'm just going to leave it as 3/4 for now. Over here, you'd have kind of the same thing. We'd just take the square root of both sides and get sine x, and we would have plus or minus root 3/4, same thing. So let's go ahead and simplify that, because if you're looking at those points around the unit circle, you're looking at those y coordinates. You're not going to find root 3/4, at least not like explicitly written like that. So let's simplify it a little bit. Whenever you take the square root of a fraction, it's equivalent to taking the square root of the numerator and the denominator separately. So the square root of 3 is just square root of 3. Can't simplify that, it's irrational. So we're just going to leave the square root of 3. But the square root of 4 we can do. Okay, think about what the square root of 4 is. What number times itself equals 4, and that is 2. So notice we got plus or minus root 3/2. And just to save, maybe I don't need to save too much space here. I think what I'll do is just copy and paste. Might be the way to go. Okay. So over on the left-hand side, we'd be done, right? We isolated x, and that's all we need to do. Here we've isolated the trig function. We still need to pull the x out of here. So if I'm going to write my solutions, what I'm looking for are where the sign values are either positive root 3/2 and negative root 3/2. So if I pull that unit circle back up, what I want you to look for, here I can make it real big, is we're looking for the y coordinates where, or we're looking for the angle measures rather, where the y coordinates are either root 3/2 or negative root 3/2. So we see at the top, we've got at pi/3, I still kind of annoyed that I can't draw in here, so let me pull this up again. We're at pi/3, we do have positive root 3/2 as a y coordinate, so we know that's going to be a solution. We also have 2 pi/3. Okay, we see that there. And then we also have, what I should do? I should move myself, separate thing. Sorry. Over here, right, you can't see that. I wonder if I could scooch it up a little bit. Down here, we've got a y-coordinate of negative root 3 over 2, but that's okay. That's going to be one of our solutions. And then over here, we should have one at 5 pi over 3. So we got one at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So here we'll end up with 4 solutions on the unit circle. And let me type those out. So x could equal pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now these would be the solutions on the unit circle. So if the question is asking for just the solutions on the interval, then that would be all you would include. Let's see if I can move some of this up just a tad. Just give me a little bit more room here. So these are my solutions on the interval. And then the general solution will look just like this, except we'll tack on a plus 2 pi n at the end. And that's really the only difference, okay? So you're still finding those coordinates around the unit circle. Oh, didn't copy for me. You're still finding those those angle measures going around the unit circle, but we are going to add 2 pi n to indicate that, we just want the pi, 2 pi n to indicate that there are more solutions, whether they're positive or negative, that we can add an entire revolution to find another angle measure that has the same sine value. So depending on how the question's worded, your answer is either going to look like this or like this. And that's it for that one. In some cases, we have to factor out a GCF. So really, we're just kind of reviewing how to solve quadratics here. At the end of the day, really most of the hard problems are going to be quadratics. And then the only real new thing is trying to undo this trig function and find these numbers. But the actual solving process will be pretty much the same. So again, I'm going to show you the the old school way and now the trig way to do this. It'll be very similar. Here we have a greatest common factor of x, so we would factor that out. And then we would use the zero product property to, get this out of the way, to set each of these equal to 0. So either x equals 0 or x plus 1 equals 0. So the zero product property is just saying if you've got two things that multiply to equal 0, you could set at least one of them has to be 0. So we're going to basically split this up into two separate equations that we'll solve. This one over here is already solved. We just need to subtract 1 from both sides here to solve that. And then so our answers would be x equals 0, or I don't know why it doesn't let me do a space there. Come on. Come on, let me type the word or here. Or there we go. Sorry, guys. Or x equals negative 1. So we get two solutions. It's okay if you type it like this, or you write it x equals 0, negative 1. That's acceptable too. Those are your two solutions, right? So this one's pretty straightforward. Now, when you have a trig function like that, you do kind of the same thing. You're going to factor out your GCF, which in this case would be sine of x. So we'd have sine of x times, I might use brackets here just so that we can differentiate the parentheses with the brackets, sine of x plus 1. And so the solving process is pretty much the same. We're going to use the zero product property to split these two up into two separate equations. One being sine of x equals 0. And all of a sudden we turn blue here. There we go. Either sine of x equals 0, or we have sine of x plus 1 equals 0, which if we change that, or if we solve this, we need to subtract 1 from both sides. So we're going to get sine of x equals 0, or, just write it out, or sine of x equals -1. So we are going to be looking for where sine is equal to 0 and where sine is equal to -1. So if we go to our unit circle, we're looking for where the y-coordinate is either 0 or -1. So right here, the y-coordinate is 0. So 0 will be one of our solutions. Here the y value is 1. You can't see it. Let me drag it down. Yeah, the y value is 1, so we're not going to include that one. The next one should be over here. Yep, so our y value is 0. So pi is going to be a solution. And then finally, 3 pi over 2 should be another solution because the y value here is -1. So just to kind of recap here, we got 0, we got pi. Both of those are where y is where the sine value is 0. And then the last one here, when the sine value is -1, will be 3 pi over 2. So we get x equals 0, x equals pi, or x equals, what was the last one? 3 pi over 2. And that would be the solution if all I'm asking for are these particular solutions. Okay, if I'm going for the general solution, then I'll write it just like I've been writing the other ones. Come on. Doesn't want me to copy this. There we go. Okay, so we'd have these 3 solutions on the unit circle, and we'd write plus 2 pi n. And that would be how we would write the general solution. So yeah, you can see the solving process itself is very similar to what you've done already. It's just the new thing is just trying to figure out what angle measure would make that true. All right, I've only got, I think, 2 more for you. Let's see what we got here. So this next one is going to be a factoring problem, and so you might review some of the previous videos I have on factoring. If you really struggle with factoring, you might even go back and review my Algebra 1 video where I go over exactly how to factor. At this point in precalculus, you should know how to factor. Maybe you practice a little bit. Maybe you need a little bit of practice, but for the most part, I'm going to assume this is something that you're coming with me knowing how to do. So this one would factor as 2x plus 1 times 2x minus 1. I'm sorry, x minus 1 equals 0. And so here we can use the zero product property again, just like in the last one. And we're going to set both of these equal to 0. Here we have, let's make sure, okay. We've got 2x plus 1 equals 0, or x minus 1 equals 0. And then we would solve this. We would subtract 1 from either side and divide by 2. So we'd get -1/2. Over here, we would get x equals 1. So these would be the 2 solutions we would get, and that would be our answer. Okay. Over here, we would do it kind of the same way. Okay, so notice like when you're solving this, you're going to treat like this trig function like it was its own variable. Okay, like see what we have here? You see how these are the same? Or not the same, but they're similar. So we're going to solve it similarly. We're still going to factor like we would normally factor. It's just instead of having x, we're going to have sine of x. So here we would have 2 sine of x plus 1 times sine of x minus 1. Let's get some parentheses around there. One thing that you'll see on a lot of these problems is you get to a point where if you're writing sine of x, and this is pretty common in different textbooks, it's okay if you don't write the parentheses, okay? In my opinion, it's not the greatest notation, But if you just see like sine x, these are the same thing, okay? I will try to always put the parentheses around there just to stay consistent. But I think I think the homework is kind of an older homework, and if you look at textbooks, they'll usually write it without the parentheses, just to avoid this issue where you have like just so many parentheses to worry about. So anyway, you're going to set both of these equal to 0, and you're going to get similar results to what you had over here. So we'll have like 2 sine of x plus 1 equals 0. And we'll also get sine of x minus 1 equals 0. We'll solve this and get sine of x equals negative 1/2. We would use the same technique. We would subtract 1 from both sides and then divide by 2. And then over here, we do the same thing and we would get 1, right? So I might as well just stay consistent here. No shortcuts. Sine of x equals 1. So we're going to be looking for, there'll be 2 angle measures on the unit circle where this will happen, and there'll be just 1 point on the unit circle where this, or 1 angle on the unit circle where this will happen. So let me just go ahead and pull up that handy old unit circle. Now it's kind of big. Let's make that a little smaller. Get it kind of out of the way a little bit. So if I'm looking to see where sine of x is equal to negative 1/2, that would be at the angle measures. Let's see, so I'm looking at a y coordinate. I see one at 7 pi over 6. And I see one at, let's see here, the next one where it's negative 1/2 would be 11 pi over 6. And then if I try to find where sine of x is 1, that's where the y coordinate is 1, that's going to be right at the top at pi over 2. So these would be the 3 angle measures that would satisfy the equation that exist on the unit circle itself. And if we want to give the general solution, we would just tack on the plus 2 pi n. Again, I'm usually not going to ask you for both of these. I'll usually just ask you for one of them. Either the restricted solution or this general solution. So really the last thing I wanted to show you guys on this is how to deal with the reciprocal functions, because it's kind of a pain to, it's a little bit easier to solve these when they're, sine or cosine are just like right there in the unit circle. But if you have something like cosecant or cotangent or anything like that, and you got to start thinking about reciprocals, I want to show you how you can rewrite the equation so that you don't ever have to deal with that, where you can just change it into either a sine or cosine and go from there. Ooh, let's get rid of that unit circle. It's kind of blocking everything, huh? There we go. Okay, so last problem for today. So let's say we have something like this. This is not going to require any factoring. We're going to solve it just like we would solve it if the trig function was something a little bit more familiar, if it was sine or cosine or tangent. It doesn't really matter what it is. But we're going to go ahead and add 4 to both sides, which give me 2 times the cosecant squared of x equals 4. We would divide both sides by 2 here. So divide by 2, divide by 2. And we would get cosecant squared x equals 2. This is where we would want to, sorry, I'm losing my train of thought here. This is where we want to get rid of the squares. So we want to take the square root of both sides, and we'll end up with plus or minus. So we'd get cosecant, just cosecant of x equals the square root of 2, and that would be plus or minus. Anytime you take the square root of both sides, you got to do plus or minus. Okay, so where is the cosecant plus or minus root 2? It's not as obvious when you're looking at that unit circle. It's a lot easier if you have like an x or a y value for dealing with sine or cosine. So the way to deal with this is to reciprocate both sides of the equation. The reciprocal of cosecant is sine. And the reciprocal of root 2 is 1 over root 2. So I'm just going to rewrite this as plus or minus 1 over root 2, which again is not something you're going to see on one of those coordinates because it's not rationalized. So we do have to rationalize this. So if I multiply both the numerator and the denominator by root 2 here, I'm going to get 2 over root 2, root 2 over 2 rather. So what we're looking for here for our solutions is all of the places on the unit circle where the y coordinate is root 2 over 2. And now let me go ahead and bring that back up. We can see that's going to happen at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. In each case, we've got either a positive root 2 over 2 or a negative root 2 over 2. So, you know what, I'm going to try to squeeze this back up just a little bit so we'll have a little bit more room to write our solutions. Move that up a little bit, that up just a little bit. Just going to kind of squeeze everything up here just a tad. Okay, so let's go ahead and write our solutions here. We'll have x equals pi over 4. Okay. And we've got 3 pi over 4. We've got 5 pi over 4. And finally, 7 pi over 4. And those are all the solutions on the unit circle itself. And so that would be like our solutions on this particular interval. Oops, what am I doing? Oh, I lost my cami. No, I don't need any of that. Misclick. Sorry, guys. Okay, so, yeah, no, I don't want to have to retype all this. Okay, so that would be my solutions on that particular interval, and if I wanted to include the general solution, again, you know, probably tired of hearing me say the same thing over and over again, but you're just going to write the same solution set, except we are going to add that plus 2 pi n. We're going to stick that on the end of it. You'll pretty much never have to write both of these. I don't think I'm going to ask you to write both, like for the same problem, but you want to, you know, I don't know if it's half and half, but there's a section on the homework where it says just give the solutions in the interval, and then the other half says, you know, write the general solution. So it would look like that. And that's it for today, y'all. Next time we'll start looking at some identities and see how we can use those to solve different types of equations that might be a little harder than the ones we're working with today. But other than that, let me know if you guys have any questions, and y'all have a great day.